Hello, let's talk about a Liskov substitution principle. It's one of the things that is commonly mentioned in software engineering debates about architecture and about bugs, and it's a thing that you will encounter quite a lot in very different places. So basically, what kind of problem are we solving here? It's a problem of subtyping. So we have some kind of type, let's call it T, and we have another type called S, and then we want to say that S is a subtype of T. But what we actually want in this case is substitutability. So we want to use a term of type S in any place where a term of type T is expected. And there are different kinds of subtyping: nominal, structural, behavioral, whatnot. The Liskov substitution principle is about behavioral and very strict behavioral subtyping. This problem was exposed and also resolved in the keynote at a conference called OOPSLine 1987. The conference still exists and is run every year. Now it's a part of a bigger initiative called SPLASH. A couple of years later, there was a paper in a journal called Topless Transactions of Programming Languages and Systems. Again, it still exists and remains one of the top journals in programming language research. On the left, you see Barbara Liskov, a person who was responsible for the keynote as well as the paper. On the right, you see Jeanette Wing, who was a co-author of the paper. So the principle itself is very easy and very straightforward if you think in terms of sets. So S and T are types, so basically sets of possible values. And you have some P, some predicate that holds for any term of type S. So for all elements of set T, P holds. And then basically we want to say that P should hold for any term of a subtype. And it makes perfect sense, because if you have a set, and if you can prove that for all elements of that set something holds, then obviously this holds for anything that is a subset of T. So, and that subset is then called a subtype. So closer to software engineering, we have a program P, and it's defined in terms of a particular type. And what we want is that behavior of P should remain absolutely unchanged if we use terms of type S instead. And if this holds, then we really say that yes, S is a proper, good, strict subtype of T. Another reformulation, even closer to software engineering, is like this. Functions that use pointers or references to base classes must be able to use objects of derived classes without even knowing it. This reformulation belongs to Robert Martin, or also known as Uncle Bob Martin. As painfully obvious from this picture, he is one of the coolest people in software engineering. He is responsible for reformulating the extreme programming fad into the agile movement, and he wrote a book, Clean Code, and is responsible for many other things. An example of subtyping. Let's say we think that integer is a subtype of float, which means whenever a float term is expected, so whenever we have a place in an expression which, or around a call to a function which should use a float, we can use an integer. So the motivation for this is arithmetic, so we can easily downcast it or upcast it, whatever. Whenever we have an integer, we can always go and create a float out of it by adding .0. But let's consider this example. We have two things that classify the same thing, which is movement. Specify it in terms of kilometers per hour, which is usually referred to as speed, or minutes per kilometer, which is usually referred to as a pace. So, for example, if you have a speed of 6 kilometers per hour, it's the same as a pace of 10 minutes per kilometer. So, obviously, if you're walking at this pace, then in 10 minutes you will cover 1 kilometer, in 20 minutes 2 kilometers, and so forth. and in 60 minutes, so in 1 hour, you will cover 6 kilometers. Let's define this function, which takes speed and returns pace in Python, and it does return 60 divided by pace. So then we run it for 5, so it's 5 kilometers an hour, 12 minutes per kilometer. Perfect. For 6, also perfect. For 7 and 5, also perfect. It says that it's 8 minutes. And then we run it for 61 kilometers an hour, and then suddenly our pace is 0. But if our pace is 0 minutes per kilometer, then we are moving at infinite speed. And basically, any speed higher than 60 is undistinguishable from infinite speed because, well, because this Liskov substitution principle is violated, which means that in Python, if we think in terms of types, which is not always what Python does, then integer type is not a proper subtype of a float. Another very classic example is square and a rectangle. So suppose that we have, in this case, a C++ program, and it defines a rectangle like this. So you have public stuff and you have private stuff, and private is basically a width and height of a rectangle, and you have getters and setters for it. And then we have a square, which is a subtype in a sense of inheritance. Square is a rectangle. So this is a relationship is usually represented then as inheritance. So we inherit from rectangle. We have a class called square, and we do some stuff with probably setters, so that whenever you set width, you also set the height, something like this. But the thing is, whatever you do, you will encounter many subtle bugs. So there will be some external code which would expect, if you set width, it would expect the height to stay the same. And unless set width and set height were declared virtual, you will also, especially in C++, you will get situations where you call a function set width from rectangle while you are in fact operating on a square, and this will lead to inconsistent squares, to squares which are actually not squares but rectangles. But in any way, any code that expects certain stuff, in this case this width and height consistency, any code will be broken for squares, because a square is not a rectangle. In conceptual, square is a rectangle and integer is a float, but the behavior of an integer value, and in particular in Python, but in other languages I guess as well, not in all of them, definitely not. This behavior is not consistent with the behavior of a float, so it is not a proper subtype. Again, with square and a rectangle, the behavior of a square object is not consistent with the behavior of a rectangle object. So in general, when you want to respect the Liskov substitution principle, you need to keep invariance. So if you have something that always held for any object of a type, in your subtype it should still hold for everything. This is a direct consequence of the principle. Then, if you have if you think of methods as having preconditions and postconditions, do not strengthen preconditions. This will also violate the principle, and also do not weaken the postcondition. So, if you run a method in a subclass, it should not be more demanding on the input, and it should not do more or allow more in the output values. And you should not, in any case, allow objects, states to reach some situation which would be inconsistent with the supertype, which would have been impossible with the setters, basically, of the supertype. This is very related to design by contract by Bertrand Meyer, and it is a part of a solid paradigm. So the L in solid is Liskov substitution principle. Summary is that this principle explains what a good subtyping is, and when should you think of two classes as having subtype supertype relationship. It is quite often broken if you do things without thinking and without asking the questions that arise from knowing this principle. And when it is followed, it requires more careful design, and it also leads to more stable systems. That's it for now. Thank you.